is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey there, everybody. Welcome, welcome, welcome. It is I, Mark D'Antonio, here with, of course, our good friend Daryl Mason. Hello, Daryl. How are you?
Hello, Mark. I'm good, thanks. You? Hello, everybody.
I'm good, thank you. It's a great night, and we're going to have a good time listening to the music and looking at the sky. So it's going to be fun. Hopefully you guys are willing to hang out with us for a while. Looking forward to it. We got a bunch of things to show you. And I know that Daryl is interested in a few objects that he already asked for. And that's going to be of primary importance to us. So we'll be doing that as well. I'm just getting some last minute things set up here. I'm sorry Papa Tom had to leave. He couldn't stick around with us tonight, but you know what? That was very nice of him to come in, wasn't it? To say he couldn't be here with us tonight. That was very nice. That's very nice. So, we are here to look at the night sky, and right now, if you look at our screen, this is Orion the Hunter, and as you can see, Orion is like pretty much a dead center in our screen right now, and it is a major constellation of winter, along with Taurus the Bull up here. And in Taurus the Bull, something we're going to look at here right in just a few minutes is right up here. We're actually kind of near it right now, and it's right up about here, and it'll show up. There it is. I went through a focusing run already. So
Messier 2.
one.
I know. Small joke, very small joke.
I must have missed it.
Messier 1.
Yes. Exactly. Yeah, we're going to look at Messier 1. Messier 1 is a exploding star, a supernova that, it exploded in 1040 AD. Seen
1054.
1054. What did I say? 1040. I'm sorry. I'm thinking tax day. I'm thinking taxes. Wow. Yeah, thank you. 1054 AD. Seen
Another small joke.
Another small joke, yeah. Very, very small. Seen by the Chinese primarily, and that was a noticed object in the sky at night, but it was also in the daytime. So it was bright enough to be seen during the day. And I'm going to tell the telescope to head there now, so we're heading there right now. And you'll see that start to move here, and you'll watch up here, and you'll see the telescope moving here in just a minute.
You know, we were talking about supernovas the other night.
Yeah.
The last supernova that happened in our galaxy that we got a good look at was Cassiopeia A, I believe.
What about 1987A? I mean, technically that was in the Magellanic Cloud.
Right. I'm talking like a galaxy, a supernova right in the galaxy, though.
Yes.
And interestingly enough, if I remember correctly, it happened right before Galileo started pointing his telescope in the heavens.
That's
and we
interesting.
haven't had a good one since in our galaxy.
We will. I read some research just today that suggested that Betelgeuse is actually closer to exploding in a supernova than they think. Instead of 10,000 years, they think it may very well be something on the order of 100 years.
Huh.
Yeah. Pretty cool. All right, let me just move this here. I'm going to, first of all, I got a couple of setup things here I just have yet to do. Do them right now while I got you on the line with me, guys. I'm going to set our correction values for east-west motion, which is called right ascension. And then I'm going to set our declination settings. Okay, hold on a sec. All right. Waiting for our system to come back alive. It hasn't come back to us yet. All right, I'm going to come out and come back in because I don't like what that's doing. Taking too long. And I'll take care of you right here, Daryl. How long is this? This should be okay. Where are you? There you are. And now I will go back to sharing the screen with you, Daryl, because why not? You're okay sometimes. There you go. All right, and now we should be able to go here and then go down here, set our right ascension or east-west rate, and I set that to 15. And then I set the north-south controls, the corrections, to 22. Uh-huh. And then we're done with that. Okay, and now I head down to this next one and turn off this high precision mode, which I have found is less helpful than it used to be. So that's good, actually. All right, and now we come back to our guiding mode here. And what I'll do now is come back to our stellarium and tell it to go now to the Crab Nebula. And it'll move up there, and the Crab Nebula will be right in the view. And it should pop in. There it is, right there. There's a way around everything. Okay. Hey, Calabos is here. That is Michael Tarr. Hello there, Calabos. How are you? And how is Tiffany? Your better half. She'll be happy I said that. Okay.
The War Department, in other words.
Oh, that's funny.
The old ball and chain.
Oh. Well, no, she's less of a ball and chain and more of she's a very nice person, so I can't call her a ball and chain, actually.
I'm sure she is. That's why I'm a confirmed bachelor.
Well, yeah, that's a problem many have.
That was a joke on the Benny Hill show many years ago.
Yeah.
He was playing a game show with the little old bald-headed guy.
Oh yeah, the one he pats on the head.
Yeah.
Yeah.
And Benny was the game show host, and he was asking Smarty questions, and he goes, "What's the definition of a confirmed bachelor?" And a little old man goes, Why? It's a man who has never seriously considered marriage." And Benny buzzed him wrong and said, "Wrong. It's a man who has seriously considered marriage."
That's funny. All right, let me come back here.
Marianne is here.
Marianne, hello. Yeah, that's
Marianne.
That's our Marianne. Okay, I'm gonna set the speed. Go to here. Okay, and no, wrong one. Sometimes Starlink is wonderful and it gives us everything we need, and then sometimes there's not enough satellites to give us what we want. Now, right now, we have a little issue with satellites, but as the night wears on, they're going to get better. That's out of our control. Right now, we're going to go back to the Crab Nebula here.
Bonnie's here.
She was here before.
I know. She's so nice, I said it twice.
Okay. Hello, Bonnie. Hi, Marianne. Actually, I want to say hello to everybody that's here, that's come to join us. JSCO 77 was the first one here. You got to use that telescope, man. Can't wait to hear how it looks. Then Bonnie was here on a Hada 77, yeah. Papa Tom had to leave, but he came in to say he couldn't stay, which was nice of him. Eric's Automotive's with us. Daisy and Zoe. Hi, guys. And then Tim F. is here. That's fine. That's great to see you, too. Genghis is with us. Hello, Genghis. And Dagger. Hey, Dagger Spells is here. I haven't seen Dagger in a long time. It's very nice to see you. And Genghis, I think I said hello to you. Rascally Rabbit's with us. Sam S. is with us. Nice to see you. Donald Kunzer. Good to see you, too. Mr. Django, here from Belgium. That's Mr. Django, yeah. That's Stefan. Stefan did a gorgeous photo that Izabela put up for us earlier. He photographed a sunspot group, Daryl. I don't know
Yeah, I
if
saw that.
wasn't that fantastic? Didn't he do a nice
It
job?
was. Yes.
Very nice,
I-
Stefan.
I thought I recognized it. There's a whole bunch of them up there right now, though, so it's kind of hard to
Yeah,
tell them apart.
yeah.
Wanted to say it was Spot Group 3576.
Might be.
But there have been some other good ones since. I
Stefan,
think 70,
Stefan, tell
76
us.
is going away now.
Stefan, tell us which one it was. And Stefan's Mr. Django, by the way. And then let's see. MPG is with us. Hey, MPG, how's it going? Tiffany is with us as well. That's the good side of Calibos. You know. All right. Alice Pooper's with us too. All right. Now here is Measure 1. This is the Crab Nebula, and we have been looking at the Crab Nebula for well over 150 years with telescopes, and we've actually taken photo after photo after photo, and by putting them all together, we've actually been able to build a amazing time lapse of the expansion of the Crab Nebula. Is the coolest thing, and that's really a beautiful video to watch. It's short, but you get to see the Crab Nebula just going expanding outward. And I see this little white line here. I don't know why it's doing that. I am signed in. I don't know why it's doing that to me. Little problem, but whatever. I don't care. We'll fix it. All right. So that said, let's start now that we're tracking. Let me just go here to make sure we're tracking. Let's go see. And yes, we are. When you see these numbers, that tells you the fractional tracking that we're doing. If those numbers ever climb above 2, then we're probably going to get some kind of a wind that's blocking us or making us get an image that will not be retained when we make the stack. All right, so yeah, Mr. Django says, thank you guys. Yes, the sun's very active now. And again, for the moment, it's Belgium weather, rain. Sorry to hear that. Okay, we're going to do 25 seconds here. All right, just a minute.
That darn heart is right in the way. Shirt. Marianne said, design our new STLS shirt. I couldn't tell what the last word was.
Oh, yeah.
Because that heart is right dead in the way.
Yeah, here's the thing. We're having a contest to design a new SkyTour live stream shirt. It's going to say skytourlive.org on the in the upper part of the shirt, left or right. I don't remember which side. Marianne knows. And what goes on the back, we're thinking we're going to put the universe live in real time. And as far as what we put, anything else, we'd like to have your input on it. And if you guys give us some ideas, anyone that has an idea that we use, we will then send you a free shirt.
Astronomers love heavenly bodies.
Yeah, I've seen that one. That's a good one.
I break for black holes.
That's funny too.
I break for naked singularities.
Boy, you really want a shirt, don't you? You'll get one.
Yeah.
All right. All right, so this is, yeah, that'll be our Crab Nebula shot. And so we're going to be working on that right now. So our second exposure is coming in. And we have a bunch of safeguards in place to prevent our imagery from being bad imagery, winds shaking the telescope or whatever, and lawn gnomes that go in and start banging up against the telescope and shake it. That filter we're using is a full width half maximum filter, And there we go. See, that's our perfect one right there. And what it does is it makes sure that the stars are of a particular roundness, and if they're elongated in any way, it will reject the image and not use it in the stack. So in this one where we just took, okay, and the second one it took, they were all used. As you can see, the stars are nice and round. Let's do a little image processing here to start bringing out some of the color of the Crab Nebula. We can already start zooming in. This is an extremely dangerous area in space to go to, so I'm pretty glad that we're here and not there. Because right in the middle here, you'll see coming in very soon, right there, okay, that is a neutron star. That neutron star is the remains of a star that went supernova. And that star that went supernova is what blew out all this material into space. And a lot of things happened during a supernova, and I won't dive into too much of it, other than to say that all the stuff you're made of came from that guy right there, that type of guy right there, a supernova. Many of the elements in your body were made once in the heart of a star, and in the subsequent supernova explosion were scattered to the universe to drift around the galaxy for billions of years until Earth was formed from them, and then organic molecules were formed with them, and then life, which is you. So these areas, as hot and as absolutely foreboding to go to, are the areas from whence life would spring eventually. This is the starting point, a supernova. This supernova also sends massive amounts of matter out into space at a high speed, and that causes shock waves. That is to say, like a snowplow pushes snow, well, the outgoing material is pushing other material that's impacting it. So as it hits more material, it pushes it along, and that tends to compress it, which tends to potentially cause star formation. Now, how can that happen? Well, that can happen because we're talking about an object here that is light years in size. It's not just like 100 miles across. It's thousands of light years away. And I think it was, how far away is this? I want to say 6,000, but I think that's too much.
I forgot offhand.
Okay. Michael Hedrick, hello. C&D Boy, Dean Bostador, how are you guys? Yeah, so as we zoom in now, let's start to enhance the color and the darkness. And first thing I'll do is I'll use a special enhancement trick that we have available to us. You can see a lot of the sharpness come in. There we go. And there you see, I'll show it to you right now. This guy right here, that is a neutron star. Inside that square, that white dot. What's interesting about that neutron star is that it is literally thousands of light years away, and it's only the size of Manhattan Island, and we can still see it. This has to do, of course, with the fact that this object is so intensely bright, giving off a lot of its light in ultraviolet, which is, of course, very, very higher frequency radiation. And so the ultraviolet light will tend to ionize any atoms, knock the electrons off. So it's knocking the atoms off of the oxygen, which is this green part in this nebula. It's knocking the electron off of the hydrogen atoms, which are out here. Okay, and when those electrons eventually bounce and fall back into the atom, they give off the light that they absorbed. But they give it off in different wavelengths than the ultraviolet wavelength they receive to make them go off the atom. And oxygen gives off green light when it's ionized if two of these are ionized. Two electrons are ionized. And hydrogen gives off red. And those are the predominant colors. There's other colors, but these are the two main ones. We have green from the oxygen, doubly ionized oxygen, which is known as O3, and the H2, which is the singly ionized hydrogen. It can't be more than singly ionized because it only has one electron. So only one electron can go off and head up. Hello, Christine Anderson. Nice to see you.
Michael H. asked you a question. It's off topic. It's not about the crab. The comet's.
The comet begins with a T.
Yeah, Suchinshan Atlas, C2023A3.
Okay, is that within our line of sight right now?
Well, it's 300 million miles away, so it's not worth looking at right now. Plus, it's in Libra at the moment, so we can't see it
anyway
this early. But, you know, it's coming in later this year, and he was wondering how big and bright it was going to be. I'm scanning an article right now. Sky and Telescope says it may become a naked eye object, so
okay.
I mean, it may be a good comet, maybe not a great comet.
All right. Well, we'll be on the lookout for it. If it becomes a good comet, we will check it out. We will definitely check it out. I'm going to try something here.
Looks like it's going to go away, then it's going to come back. Closest approach to Earth happens on October 12th.
Okay.
So we'll worry about that in October.
Very good. That's a long way from now.
Oh.
But it's all right. It's all right. Okay. Got rid of my annoying thing there. Okay, so right now, what I would like to do is we've got 17 photos we've taken of this right now. You can see them right here. Right, where's it? Right there. 17. No, 18 now. Right there. Right there. See? 18. Okay. Our progress bar is over here. This is the progress on our exposures right here. So that tells you where we are in our exposure. This is our telescope control right here. Okay. That's what you see north, south, east, and west on there. And then values for the telescope computer. This is the telescope computer view. Right now, it blanks out after a period of time until I start using it. This is the telescope out there in the building. When I say out there in the building, I mean 2,500 miles from me. I'm in Connecticut right now, and it's out in Arizona in the middle of the desert. That's got to be pretty freaky for like creatures in the desert who come in and, you know, they look up and all of a sudden this roof rolls off and nobody there to make it happen. Pretty strange. You know, this is our stacking setup here. This is where we actually build our images. We'll actually take an image, take a second image, and align it with star to star with the next one, and stack them on top of each other, making an image sandwich. The more we do that, the more details come out. Like we can now see a lot of these little filaments in here, and it allows us to zoom in on this even more. And now you can see the neutron star in here very, very clearly right there. Right there, look at that. Okay, so then over here is our one of the most important settings is exposure right here. So that's 25 seconds right now, and then down below it is gain. And the gain, all right, what you see right here, that is the sensitivity of the sensor. And so coupled with the exposure time, the sensitivity of the sensor will determine just how much data we get. Now right now I'm running at a gain of 300. This is a very high gain for this camera. This camera is best at 100 gain. and we're doing it 3 times that amount because we want to capture some faint data. We'll get rid of the noise later. What's the noise? Well, it's all this stuff you see in here, this modeling. If we zoom in, you'll see very clearly what I'm talking about. There's the noise, and once the screen normalizes, you'll see it all. Okay, so now you actually see there's a crab. Yep, but we have all this other extraneous stuff, and that's noise. That's there's lack of data there. When we have data, you'll notice there is no noise. Interesting, right? And also, by the way, you'll notice, and it's hard to see, but you'll notice that this star in the middle, neutron star, is actually bluer than the rest of these stars here. And that's because it's extremely hot, and blue is the hottest color in the universe. All right? It's blue, then it's white, then it's yellow, then it's orange, then it's red. Okay? So it goes from blue hot down to red hot. All right? So there's that supernova now. It's in Taurus, the bull. And you can see the filaments and the details. It's really something. It's looking nice. And I'm going to enhance those filaments just a little bit.
You read my mind.
There we go. Look at that. Now you can see I've added what's called an unsharp mask. It's something we can do in processing as well. But it will also be saved. When we save it, it'll be saved with all these particular changes we make as well. And we're going to do another color correction. There we go. Now you can see the red hydrogen. You can see the green oxygen and the combinations of the two. There's other elements in this cloud of debris that's racing outward. But it took about 100 years to actually see significant movement. And when I say significant movement, it went from about here to about here, you know. But again, this is several light years in diameter. Remember, this is a spherical, roughly spherical object. So it went in every direction, not just two. So there's the stuff that's here is coming right at us. The stuff over here is heading that way, and that way, and that way. The stuff behind that star is heading away from us into the page. Okay, so we can't forget that the universe is in 3D. All right.
When we see that neutron star near the center of the cloud, as Mark said, it's thousands of light years away. But we can see that star, and it's only about 8 miles across. We can still see it.
Size of Manhattan Island. Yep. It's also spinning quite rapidly. You can't see that here, but this star has hotter locations on it, and these hotter locations give off radiation, and we see when that star turns toward us, it sweeps through our field of view, and so you basically see that lighthouse beacon as it passes us. So you get like as it goes around, but it does it 33 times per second. All right. An 8 or 9 mile diameter star is spinning at such a rate that it's spinning 33 times per second. And you think that's a lot, right? It's not the record for a neutron star. We've found spin rates of neutron stars that are well over 700 revolutions per second. Now, you know, we've seen on YouTube videos of people spinning things really fast until they just disintegrate because they can't handle the forces. Well, what's holding this together? What is holding that neutron star together if it's spinning so fast?
Gravity.
Yeah, that's exactly right. I was posing it, but yes. We look at the gravitational force. If you take a teaspoonful of the material that a neutron star is made from and you bring it to Earth, which of course is an impossibility, it'll weigh several billion tons. Billion with a B, as in oh boy. Okay? And so a neutron star that's, say, 8 or 9 miles in diameter with such dense material, it's going to have a lot of mass and therefore a lot of gravity. So it's going to have a force holding it together that's very, very much stronger than the force trying to fling it apart and it's spinning. You know, and so and the thing is, why doesn't it collapse further? Well, it doesn't collapse further because it's made of neutrons. That's why it's called a neutron star. Where those come from is a topic for another talk, which I can give you. But the neutrons are packed so closely together that they can't be packed any closer. And the star isn't massive enough to shrink further past that neutron pressure that's holding them up. It's like you being put in a crowded elevator, and you get in, and you're like the last person that could possibly fit. If you try to fit one more person in an elevator, it's just not going to work, unless they use some type of a mechanical press to destructively crush you and make more room in the elevator. Well, a neutron star is like an elevator full of people, right? You can't add any more people. If it was more massive, then it's like that press came in and compressed everything, like the garbage compactor in Star Wars, and crushed everything down to a smaller shape, and then you could put in more stuff. In a neutron star's case, when you crush it further, the only place it can go is to that unbelievable oddity called the black hole. And this one is not big enough for a black hole, but it is large enough to be seen from thousands of light years away, and its neutrons are packed so densely together that its own gravity holds it together, but it's not massive enough to continue past what's called the neutron degeneracy pressure, which is the pressure of the neutrons pushing out. In a white dwarf, it's a similar situation, except it's not neutrons, it's actually electrons. You can't have the electrons packed closer together than they are in a white dwarf. If it's more massive, all right, then you can. All right, and the white dwarf maximum mass, the white dwarf itself is 1.44 solar masses. Beyond that, it can go further and go into a neutron star. All right, so it's pretty interesting how this all works.
If you took that,
yeah, go ahead.
if you took that spoon of neutron star here on Earth, it would disassociate instantly, because it doesn't have the whole gravity of that huge neutron star to keep it in check anymore.
Yeah.
That teaspoon of matter would disassociate instantly, and bigger than every atomic weapon on Earth. I don't know if that'd be enough to make the blow up the Earth itself. Might, but that would be one humongous explosion if it did.
I think you're right. Yep. Donald Kunzer asks, is there an audio recording of its pulse? Yes, there is. If you look up in Google, Crab Nebula or Crab Pulsar, Pulsar, you'll get a recording of it, and you'll see a flash of light, and then you'll hear a sound that's a synthetic sound, of course, because sound can't travel in space. And they basically add a sound to the pulse of the light. When it gets bright, they add a ch, and when it goes away, they take it away. So you get a ch, 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 and it's happening at 33 times per second. So you got to check it out. It's really neat. So
MPG asked what's the closest neutron star to Earth, I believe. And a quick look, Google is your friend.
Yeah.
They list a couple, two of the closest known neutron stars. All they have is they're not named. They just have letters and numbers. They're both about 400 light years from us. One is 400, one is 424.
Yeah. And for reference, the Pleiades are about 400 light years away.
Yeah.
So it's not really close enough to hurt us. Okay.
When you were talking a minute ago about neutron degeneracy pressure and electron degeneracy pressure, and the difference between a white dwarf and a neutron star, Well, when you take that next step from white dwarf, increase the mass enough to become a neutron star, it's, correct me if I'm wrong, Mark, but it is basically squeezing the electrons so hard under the protons that they become neutrons.
Yeah, that's the process. It's actually it's a process that we should talk about with everybody. Maybe in the radio show, Daryl. That might be a good time to do it.
All right.
So remind me. I'll bring up that talk I have on all that as well. Look at this, guys. This is beautiful. And for those who don't care about neutron and electron degeneracy pressure, maybe you just care about the beauty of the universe. Well, there you go, right there. Got something for you. And by the way, I'm going to hit save now. And for those that may not be familiar or remember, we hit save, and this FITS file is being made. That's an astronomical file format that you can also get readers for if you want, but you don't need to. You can also get the PNG file, which is like a JPEG, except it doesn't have the compression that JPEGs have. And you'll get this file exactly as you see it with the colors of the stars and these colors here. This is exactly what you'll get in a image that you can use and enjoy and get. Now, where do you get it? You get it right here. I'll show you. If you go up here, this is SkyTourLive.org. See that? SkyTourLive.org is our nonprofit organization. We are committed to building telescopes around the world. We've got one in Arizona right now. We're ambitious. And we have a second one going in out in Arizona. A third one out here that may become a solar facility to look at the sun. And then we're looking at making a mobile observatory that we can take around the country to colleges and towns and cities and give people who've never seen anything under their light-polluted skies a treat of a lifetime so they can see what's up there behind all that light pollution. And that's something that Marianne, who is in the chat here, she's one of the officers within the SkyTour livestream group, as well as Tara Diulis. And we guys like Daryl working with us, and Izabela, who helps us daily, and folks like Ronald, ERT Radio, who are our patrons, and John, who is another patron of ours. These guys and folks are all just dedicated to educating folks in astronomy. You know, we do this because we love it. So go to SkyTourLive.org if you want to get this photo, because when I hit save, like that, like I just did again, and save exactly as seen, like I just did again, right now this file is being taken out of the observatory 2,500 miles from here, going up to the satellite, and coming back down to our server we make available to you for free. And you can head there. Daryl's putting a link out there right now, which is very kind. Thank you, Daryl. And you can grab the photos. Now, at SkyTourLive.org, it's going to tell you how to actually wade into the directories. You can't hurt anything, don't worry. And how to get the imagery. It's actually pretty simple once you get used to it. Want to say hi to the Goblin. Goblin won a pair of binoculars from us a few nights ago. Well, a week or so ago, maybe more. But it was great. And those SkyTour Livestream has been giving away equipment courtesy of Calabos and Tiffany. You see Tiffany Echo in the chat here in Calabos. They are the ones behind the telescope and equipment giveaways. So when they decide they want to do a contest, they do them exclusively through us. Now we'll be at Contact in the Desert in June, and I'm going to be doing a SkyTour live stream with a studio audience out there. And if I understand it right, one of the people in the audience is going to walk away from Contact in the Desert with a telescope or something else. I have to talk with Calabos and Tiffany to find out what that's going to be. And it's there's going to be several giveaways done while we're out there. So I have a feeling we're going to be hopping. You know? Okay, good. There we are. So that's where we're going to stop with this one. 55 exposures, and if you look right here, it says total exposure 23 minutes 20 seconds. That's how long we exposed this for, and much of the noise is gone when we do that. We saved it, so it's on its way if it hasn't already arrived at our server. And we're now going to go to our next stop here. And what I'd like to do, Daryl, is I'm going to take us to something I talked to you about earlier tonight. And let me just go up here and see where it is.
Oh, that
It should still be above.
down there by the double cluster.
Yeah, right here. I gotta get
Too
here.
far for that. It kind of sits between Cassiopeia,
Yeah.
Camelopardalis, and Perseus. Right, not far from the double cluster.
Yep. There we go. Okay. This is perfect because this object we're going to look at right now is for all of you lovebirds on Valentine's Day. This is called the Heart Nebula. And we're going to run the telescope over there right now and check it out. So you watch the telescope. It's going to go looking way out over there, heading out toward the back of that building. There it goes. Yeah. Uh-oh. It's got to come back up.
Yeah. If you're having a lag with Starlink, perhaps.
Well, no. I mean, it's actually it's here. It's just that it's not. It's staring at the building right now.
I understand.
Yeah.
I mean, it is higher than Polaris right now, so you shouldn't have a problem.
Yeah, that's kind of weird. All right.
Is the top image on the left the Mead controller? Is it blank?
Yeah, I'm trying to figure out what's going on here. Might be a lag thing because we're not counting it all. So there we are. Well, it's there. All right, let me bring us back. Oh, wait a minute. It's not going to go because I'm actually, I've got to increase our speed. Here we go. Okay, hold on. We got a little lag right now. All right, now let's do this again. Yeah, we're still lagging. We're waiting. All right, let me get us out and get us back in, because that's not...
The Starlink thing?
I'm not sure if it's a Starlink thing.
What's the word I'm looking for?
I don't know. Well, I think it is a Starlink thing, but let's find out. Let's go here. First of all, okay, so it should be at its max. All right, there it goes. All right, still... Okay, you know what I'm going to do? I'm going to bring us back in using a different approach. This is going to be slightly different, and I'm going to have to correct a few placement items. This is fine. We're getting stars back at least, and I'll figure out what's going on with this in just a second.
Oh, I lost your share screen.
I know you did.
Yeah.
Just hang on. Right. Okay. All right, here we
plate,
go.
Plate solid?
No. I'm not lost.
Oh.
Yeah, I'm not lost. I'm just going to let me just get you back here too. All right, let's and we'll share. All right, we're gonna share a Daryl with all of you now. All right, there we go. So you're back. All right, so ta-da! Yeah, and I'm gonna just bring us back around now. Okay, there we go. Okay, hang on. I may have to also escort someone out of the building. Hey, are you heading out? Yeah. Okay, hold on. I'll be right back momentarily. Hang on. Okay, I'm going to go just with you because we've had coyotes out in the yard.
You don't have to go home, but you can't stay here.
Okay, sorry about that. Somebody was leaving and I had to escort them out. Someone was here late and I had to escort him. I apologize. Okay, so let's go back and see where it is that this thing thought it was going. Because that was probably... What are you doing?
Me?
No, not you. No, I'm talking about the telescope here.
Oh.
That's strange. Okay, so... All right, I'll have to investigate why it did that. Because it shouldn't have done what we just saw, you know. However, that's okay. We will get it to do its thing. First things first, I'm going to move this over. Sorry, folks, for that delay. I apologize for that. Hey there, Lisa Beaucamp. Nice to see you. Thank you for coming by. All right, and I'm going to also take this and make it smaller. All right.
There should be a box of chocolates, Nebula.
Box, yeah, exactly. All right, well, I can't, we're not going to be able to look at the heart. But what we can do is, while we're in this neighborhood, I think we can look over here. We talked about this earlier, remember?
Yeah.
So I think we're going to do... and we got several galaxies here. We're going to look at this one. We're going to look at that. We looked at the other one before. We're going to do this. This is called the Starburst Galaxy. And the telescope's going to roll around back where it was before, and then find itself back to this area. The Garland Galaxy is pretty too, so we'll take a look at that if we can.
Dean Bostador has a question of you.
Okay. Let me first get out of here. Shrink it down.
Dean, if I remember correctly, he was using HughesNet or something of the sort.
Oh, I'm using Starlink now. I was using HughesNet before. Looks like we did lose our place in the sky. Well, let's go to a bright star. Well, actually, let's see if it can find the other galaxy too, as it attempts to find it. Let's see what we get. Sometimes when it goes winding around the pole like that, it can get lost. And I might have got lost. Okay.
If I'm interpreting your telescope images correctly, the telescope is pointing northwest now, correct?
Yeah, it looks like it's sort of pointing northwest, so it's kind of like the wrong way. So what I'm going to do is
Maybe it's pointing toward the heart now.
Oh no, I'm looking right at it, and there's no. You'd see the cluster. All right. So what we're going to do, even if we get lost, we can fix it. I'm going to tell it to go to Aldebaran, and it probably won't get there, but it's going to put the telescope back in the configuration that's proper. For getting us to Aldebaran. Which is what we're seeing now. That's the proper configuration, but
yeah,
but it's not going the right way.
The heart is a good bit higher than Polaris still. I think you'd be able to get to it.
Yeah. I'm going to have to... I had to shut the telescope off because it got messed up with its directions. So I have to turn it back on. I'll disconnect here. Maybe I don't have to. Well, I'll do that. I'll disconnect anyway. But then I'll start up the telescope again, and then I'll have to go through a way to find have it find itself again, which is fine. This is what I go through every time I start up, so. And we'll start up the camera again. Get this. I'm going to leave this out here for just a moment. Donald Kunzer, have you tried hitting it on the side? Yeah, okay, good. So this is where you want to be. I'm going to connect the scope now. And it should be connected. Okay, let's see here if I tell it to go to the west right now. There we go. It's going the right direction. Okay. Right now it's lost. It doesn't know where it's looking in the sky. So we're going to fix that. Okay, and I'll show you how. Alright, so let's see here. I'm going to move this over right about to here. Okay, and I'm going to get out of this and it's going to do the GPS fix. Meanwhile, I'm going to tell it to do a... Oh, well, until it gets the GPS, it's not going to lock on, so... The star drift you're seeing across the screen is the... you're actually watching the Earth rotate out from underneath the stars. Because the telescope right now is not tracking. It's kind of cool. It's kind of cool to see. Okay. So we're all set there. So now what I can do is... I can... you notice now we're tracking. So what I'm going to do is take our tools. And I'm going to do what's called a plate solve. And it's going to solve... for this star field and tell us where we are by looking at this star field. Wow, that was fast. That's good. Okay, so let's go and we're going to go and first I'm going to turn this music down a little bit. All right, so what I'll do now is get this data and I will copy it into our telescope. I am not to be stopped. I'll tell you that. All right. All right. It says we are at 6 hours, 3 minutes, 17 seconds, which is about right. Considering we're looking to the left of Orion a little bit, I think. All right. So let's go here. I'm going to take that number. Yeah, and paste it in. Okay. Take our declination, which is minus 23. 54.27. All right. And we're going to come over here, paste this in. And 27. Oops, that was the wrong place. Okay, let me do that like this. And now if I hit sync, it should change our values here. And it did. So we are now aligned again. We now have our location. We know where we are. And to prove it, I'm going to tell it now to go to Aldebaran again. And it should go to Aldebaran now instead of going way down someplace weird.
Will you sync on Aldebaran after you get there?
Probably not, because Aldebaran is going to be... oh, wait, I got to... There it is. Aldebaran is actually a very high... oh, okay. It's... I could sync on it. I should say that. I could have said that. All right, so I have to redo some of my startup stuff, which I forgot to do. My mistake. Okay. Oh, it's doing that. All right, we don't need that. Don't need that. Okay, we know where we are. All right, what I'm going to do now is come back here and go do my setup parts again. This is stuff I do when I first start up, guys, so doing it again is no big deal. It's just got to do it. Okay, 15%. Oh, it's already set. That's good. So I imagine that maybe the right ascension is going to say 22 already. Yeah, good. Okay, and then I do know, however, that we have to turn off our high precision again, because high precision should be off by default. Okay, and then we're going to set our speed to be only 16 times guiding speed. So now when I hit the values here, it's going to move a small amount at a time. So I'm saying go to the left a little bit, and it goes a little bit. Okay, now if we come back to this and say go to Aldebaran again, now Aldebaran will be it'll be in here and it'll stay. There it is. All right. Okay, so it's gonna stop right there. So what I'll do is I'll move to the west. I have to tell you guys something. Sometimes when the telescope, because of course it's a mechanical device that will get glitches from time to time, like any telescope and any observatory. When this started happening at the beginning, when we first started doing this, I'd be in a sheer panic because I was 2,500 miles away. Oh no, what am I going to do? But as it turns out, once we started working on ways to get around problems, they just became nuisances. You have to get through them. And as long as you have procedures in place, then you should be okay. And that's what this is about right now, is having procedures in place. So we're going to bring the telescope down. We're going to center the crosshairs on Aldebaran. And then we're going to synchronize, as Daryl had mentioned earlier. This will allow us to, that's good enough, and that'll allow us to basically set the coordinates. Like, for instance, if we look at our field of view, which is this red square, okay, you'll notice that the STLS is out here. That means that the telescope thinks it's here, but we're actually looking at this, which is centered. So what we do is tell it, nope, this is where you want to be. And you'll see that the STLS now centers over Aldebaran, so we're now synchronized, and these coordinates did a final change to reflect that. So that's good. So now, let's go.
Go to the heart again if you're set.
Well, we were set before, and I don't know what it did, and so I don't know if I want to risk that. So what I will try this though. I will try coming out of this a little back out of this a little bit.
Take a baby step then.
I was thinking M82.
All right. I mean, California Nebula is even closer, probably on the way.
It might be, huh? All right. Well, let's do this. Let's.
Captain. Go ahead.
No, we'll do that. I like that idea. That's nearby. I don't know. That's actually. See where it is? There's there's a double cluster. Oh, that's a different double cluster. Where is? Oh no! I don't want to do that. I want to do what I talked about before. I want to actually go up to Bode's Galaxy. I want to do M82.
All right.
Because that's really an impressive galaxy to see. It's an exploding galaxy. We've got to see that. All right, so let's go there again. We're going to try it one more time.
Interesting. M82 is Bode's Nebula, while M81 is Bode's Galaxy.
Yeah. Yeah, and we're in the right neighborhood for this now. There it is. And there's both of them. Okay, there's M82 right there, and this is M81. I'll show both galaxies. What do you think? Oh, they're actually really pretty. So I'll bring it to here.
You
Okay.
might remember the other night, folks, we ended with Messier 81, the one
This one.
toward the bottom. Had a beautiful view of it.
Yeah. And those pictures are available for you for free. Okay, so we're going to check our focus while we're here. So I'm going to zoom in and look at the focus of the stars. Good thing I did. We can see that they are out a little bit. Okay, good. A little more. All right. Now you notice that these are little donuts, and that's because there's a central obstruction in the end of our telescope, and that's because the camera's there. But it doesn't. We have 10 inches of clear aperture around it added up, so we're good. All right, now we're gonna start doing our focus run. Now you see we have 6 stars. You'll see that number increase over there. That number's going to increase as soon as it starts to head back down. Okay, now we got 7 stars. Now we have 5. I'm going to back out because it's not affecting it. I should have probably focused in a field that had more stars in it. As it gets smaller, we're going to get more stars. As the star images get smaller. All right, there we go. And you'll see them. When we back out all the way, you'll see the yellow squares. And when we have the most stars, and when we have a curve that's made over here, okay, down here, you're going to see a parabolic curve. At the bottom of that curve, wherever the lowest point is, that's where the focus is. That's where the best focus point is. And it doesn't matter if it's sampled this one, this one, this one, this one. It's going to mathematically calculate the bottom, the minimum of that curve. For those that remember their algebra. The parabola. The STS-75 tether incident, Genghis says, yeah, you know, NASA's Unexplained Files did that, and as you guys know, I'm on a lot of these silly shows, and I say silly, they're actually pretty good. And what I did was, they took me out to Dallas from Connecticut, and they had me recreate the tether incident in the studio. So I actually built a shuttle window. I had a lens that they provided that it wasn't a mirror lens like it should have been, which is a central obstruction. There's our calculated position. I'm going to say best focus, and we'll be focused, and we can start going. And then I ended up putting a tether 35 feet across in this big studio, a very brightly lit white object. And in the foreground, I had a little mobile I made out of little bits of clay, white clay, rotating in front of the camera outside the window. And those were the ice particles simulated. And these ice particles, when you focused on them, they'd become little pinpoints. But as you focused on the tether, they would become those donuts like you saw here. All right? And they look, because they're very bright, but when they're defocused, the entire brightness is now spread across a big ring, a big donut. And so they're not nearly as bright as the tether. So when they pass in front of the tether, they look for all the world like they're going behind it. And that's the key to understanding how this all happened. So I showed that, and they were like, oh, man. I was like, sorry. It's true. Okay, you're going to see 2 of the most beautiful galaxies in the sky right now. This is Messier 82, and this is Messier 81. Let me bring our bring it up a little bit closer. Now, I'm going to set this exposure. I think we're guiding. I'm going to go here to my guide and see, yep, we are guiding well. And I'm going to set us to 25 seconds and tell it to go. And now we're going to stack this. You'll see the crab probably in here. Oh, I cleared it already, so sorry. Oh, I know why, because we restarted. My apologies. Okay. So down there you can see the yellow progress bar. Okay, when that reaches the end here, we'll have that first exposure. And then you'll be able to see these galaxies. Hello, Tricia. How are you? Cindy Murphy, how are you? Tricia Ferreira is with us, and Cindy Murphy. There we go. And now, this is just the first exposure of many to come. So, we're seeing a extremely noisy image, and that's because of the fact that the first exposure is always pretty noisy. And when the second one comes in, you're going to see a lot less noise. Okay? So, let's see what happens. There's our second one. Do you see how it got a little darker? And the detail improved. And I color corrected so the space is a little better looking. Okay, there we are. That's more of the colors. Now, I don't know if it's the moon set out there yet.
No, the moon is getting close to first quarter. It's going to set about local midnight.
Yeah, okay.
Or probably a little later for you.
Yeah. So what I'm doing, what we noticed interesting with the camera is that whenever we have a moon out, the colors of the galaxies shift a little bit more to the red for some reason. It's unknown, not sure why, but it happens. So we have to correct for that. So that's what I was doing, was correcting a little bit for it.
Yeah. Speaking of the moon, if you get a chance tonight, folks, not to take away from the live stream here, but the moon and Jupiter are in conjunction tonight, and the moon is going to pass close to Jupiter, and it's going to be a little later in the evening, close to midnight. We probably won't be able to see it then. It may set before it's at its closest, but and it'd probably help if you're in the western part of the country. But just about moonset, whatever your local time, if you could see them, you may see a very pretty sight.
Mm. This galaxy up here, let's zoom in on that for a bit while we can. This galaxy, Messier 82, is a fascinating galaxy because it appears that this galaxy has, and we're waiting for the satellites again, so we'll wait for them to come in. So it used to be called the exploding galaxy, but in fact now they call it a starburst galaxy because they noticed that this galaxy, which may be a spiral kind of like this one, but a little bit of a different morphology to it, but seen more edge on, has this incredible red central area. And I got to do this again because it's cutting out again. Let's try this again. Yeah, see? Look at that. So there it is. And let me take care of the housekeeping here while this is coming in. Okay. That was either Daryl flicking a bic or snapping his pinky finger.
Something like that.
Okay.
When we looked at Messier 81 the other night, we discussed whether 81 and Messier 82 here had gravitationally interacted, which stirred up star formation in the M82.
That
M82
is
is a starburst galaxy.
That is the current thinking. is that Measure 82 and Measure 81 have interacted at some point.
Yeah. And when we looked at M82 the other night, M81 that is, some signs of irregularities we see in it are probably also due to interacting with the Messier 82.
Yeah, let's change this a little bit to show some of the more subtle data. There we go.
You see the spiral arm on the left of Messier 81. It's got kind of a flat spot and a kink in it. That may be a sign of interaction. And the pulling out at the end of that spiral arm up toward the top of the screen may be a sign, plus the several streaks in the closer spiral arm just above the nucleus may also be indications of gravitational interaction.
Yeah. Now, M81 is probably a much more massive galaxy than M82. They are actually relatively close to each other in space, so they're not too much farther from each other. So they are truly this. So if you measure this distance to this distance, and I have knowing the distance of one of them, you can assume that the other is close enough to it, because they are basically sisters in space. So you can figure that the actual light year distance, I can calculate that and then show what may have actually been the result of triggered star formation from the interaction between the two.
M82 is, I know they call it a starburst galaxy. Is that the same thing as a Seyfert galaxy?
Well, Seyfert galaxy is an active galaxy as well. And they're characterized by starbursts, but also radiation at the north and south poles coming out. They're actually very energized galaxies. And maybe that's related to highly active central black holes. You know? Mm-hmm. But Seyferts are not quite the same as a starburst galaxy. But if we zoom in farther and farther, you can start to see some of these dark lanes in here. And you've seen in spiral galaxies, dark lanes are actually a regular shape. They actually follow the spiral arms. This galaxy has had its spiral arms disrupted significantly, as you can see, but we only see kind of edgish on, right? Hey Dale, how you doing?
Well, that dark lane looks almost like it's transverse to the plane of the galaxy, not in the plane.
It does this, see? It's going up and around and down and up. Strange. And then there's one here. Hey, Judy M. Yeah. Okay, well that's Measure 82. So this is gonna be an image of Measure 81 and M82. So we'll put them both in. As you can see, I've done this before. I have that pre-listed.
Genghis said, is that a red giant? I assume he's talking about the star to the upper right there.
It may very well be, Genghis. It's likely that it is. In the same way that other stars in here, like these down here, these smaller red ones, they could either be much further away, because again, the universe is in 3D, or they are M-class dwarfs, which are very, very small percolators. But most likely stars like this one and this one up here, that's what I was actually going to show you first, this guy and this guy, are probably red supergiant stars, more highly evolved stars. Now I want to show you something, if this will show it this early in. We've only got 20 exposures done, but this is called a push, where you start to actually show more data by pushing the mid-level toward this black level. If you notice, there's stuff down here. and there's stuff up here. You see it? Like that. So there is a significant amount of material pushing downward and upward from the center of this galaxy. That's actually a fascinating finding with this particular galaxy. Yeah, okay. So, if we now take this the other way and go all the way out here, you can see more details in this core. See that? You can see knots. You're looking at massive Orion Nebula type regions, but like many, many times the size of the Orion Nebula that span part of the entire galaxy. And you know now that you've got this dust and hydrogen gas that's ionized, the red stuff going out of the top and the bottom here. It's really something. So the question is, could there be any life in this galaxy? The answer is yes, for sure, because there's going to be a lot of dark nebula in here. And if you have dark nebula between you and a very, very hot star that has got a lot of ultraviolet radiation, well, it will in fact protect you. That dark radiation will protect you. That dark dust will protect you. It's like a shield. On Earth or on the moon, we can put a lunar colony underground and shield us from the ultraviolet radiation of the moon. In the same way, the dark dust, if it's dense enough or there's enough of it between you and the radiation source, it'll protect you as well. Here's another galaxy right here. See that little tiny guy? I think you can see that.
I see it.
Yeah.
I know from the Spanish time exposure of M81 you did the other night, there were actually quite a few galaxies visible in the background.
Yeah, and then down right to the left of M81 right here, there's this thing. It's a very faint galaxy. I think it's a dwarf galaxy next to M81. I have to look. Look at the spiral arms, though, guys. Isn't that pretty? I have to adjust colors here a little more. So here you can see the blue of the spiral arms. The blue are the colors of the young stars. The young stars are blue, and we're seeing blue here. That is because we're looking at these locations in the galaxies where these new stars form, and it's not in the center like this. It's actually out in those very active spiral arms. That's where stars form. And when they form, they're hot and young. So hot and young means blue. And blue and white, And every now and then you see knots of stars like in here. See knots of stars in here. Those are associations of stars, perhaps. An association is a grouping. And we know that in the Andromeda Galaxy, we can see what are called OB associations, O stars and B stars, that are associated with each other in the galaxy. And we see that too. Now let's just back out. We've done 29. We're going to go to 30 and stop with this one. But look at that. Look at that. Let's zoom in on that. Okay. And what I'm going to do now is, now you can see even clearer where this stuff is. Look at that. I'm going to use this. This is another histogram over here on the right. And this can show you overall what's going on with the image. And I'm going to pop that up to see what we can see. And you can see more stuff coming out of the top and bottom here. Isn't that crazy? There's a lot of stuff there. This is only a way to show that stuff. Okay. We can also invert it and go negative, like on plates that we look at. And you can see more detail going in here. So look at that. So you couldn't really even see that too well. But this is the negative. And generally what we do is take away the color like that. And you see it in black and white. That's how astronomy was done for a long, long time. Just looking at negative plates. In fact, there's whole atlases, which are just negative atlases, negative plate atlases. When I was getting my degree in astronomy, I used one. It was a German atlas called the Bonner Durchmusterung. And I actually have a copy of it in the back room here. And you can actually see all these stars. But that was from where the stars were in 1950. Another set of placements of stars was done in 2000. Okay. And then based on stellar movements now and the advances in computers, we can now use positions on the day, and it can calculate the positions on the fly where the stars should be. So we're doing that with this. We're actually calculating on day, meaning for today exactly where are these stars. And by the way, you got to keep tuning in with us and go to skytourlive.org. And at some point, we do a contest and we give away equipment. And so, although today we're not giving away any equipment, we are actually spending time with you and showing you some really cool things. Look at that. This is a beautiful standalone image of itself, isn't it?
It's not.
So we'll save this. And so our astronomical file format is saved, and now our PNG file is saved. And what are you going to get? Let's click on that. Okay, let's say you go and you look at it. What are you going to get? This is what you're going to get. That's the image you're going to get. This is what's saved in our folder, our directory. So you could see, wow, look at that. We've got that beautiful galaxy there. You can scroll down and see, wow, there's this beautiful galaxy there. All right. And this is free. You can download this, have fun with it, look at it, enjoy it, try your hand at processing. It's all kind of fun. And Daryl is sharing with you the location where the images are landing. But if you go to skytourlive.org, it'll explain where or how you navigate in the directories. Okay, it's like the second panel down. I think the third panel down shows the previous winners of our equipment. So there you go. So that's good. So we'll save this one last time and then move on. Okay. Well, that was pretty cool, huh? Even when it's like that, it looks really cool. I like this. No, I took a photo of this galaxy in 1983, and it was actually on a glass plate, part of a study. And I wonder what changed. The problem I had with it was, as I was developing it in the darkroom, we actually used film plates, guys. Okay, plates of glass, very, very thin. And when it's 10 below zero and you're developing this stuff, you can't feel your fingers. So I poked myself with the glass edges and cut myself, and didn't even know I cut myself until I saw the blood on the glass plates, like next day or hours later when I came out of the observatory and I started to feel my hands again. Things have changed radically. Yeah.
Try the heart again.
I don't want to try the heart. I don't know if I want to. Don't know if I want to do that right now, because I'm not comfortable with why it when it goes out to that direction, it caused a problem, because it's going to spin all the way around, and I'm not sure why it did what it did. But and the heart's even more southward now. I think we saw the Garland galaxy. What's this one here? There's another one out here. Have you ever seen Coddington's Nebula?
Doesn't ring a bell.
Okay. It's a very tight spiral. It's a barred spiral. We can try it. I don't know if we're going to see anything of particular enjoyment there, but we'll try it. It's right near these guys, so it should be visible in, seconds. I don't see it. Do you see it?
No.
It's probably in here. It's probably not that bright. Well, let's just do a 20-second photo just to see if it's there. I imagine it's probably there. All right. So let's go. Don't worry, we're not going to stay on this because I just want to see it. I haven't ever seen it before. I'm not even stacking at this point. I just want to see if we can see it. I don't even see it.
Michael Hedrick has a question of you.
Okay. What does Michael Hedrick ask?
Are you asking me?
Yeah, because I'm...
All right. He says, Mark, what defines a local cluster, supercluster, question mark.
Oh, well, plain and simple, it's a distance for a local cluster. Local means what you think it means. If you're talking about galaxy clusters, that's a cluster of galaxies that's relatively close to us, clearly. And a supercluster is generally a much larger cluster. And in our definition, in our space, it means that it's a cluster that's actually much further away. For instance, toward Virgo, there's a supercluster. It's the Virgo supercluster. Messier 87, where they were able to visualize and see that black hole in the center of Messier 87, was one of the central galaxies in the Virgo supercluster. Now, while it's true that we're all heading in that general direction, we are not technically part of the Virgo supercluster. We are a part of what we call our local group, which consists of Messier 33, Andromeda, our galaxy, and like 10 other galaxies in the Leo streams, and a bunch of other galaxies that are close to us.
M81 and M82 are in the local group, aren't they?
I think they are. Maybe not, though, actually. I'll have to look that up. I'm not sure. I don't remember. They might very well have been in there.
Well, if they're 10 or 12 million light years away, I do believe they're in the local group.
Yeah, I think you're right.
Let me see if I can find out.
I believe you're right, because I was trying to locate if you recall, we did a stream which did just that. It actually showcased the local group using our rendering software, the Space Engine product. If you remember. There's just so many beautiful things here.
No, they're not, evidently.
Okay.
They are the closest galaxy group to our own local group.
Yeah, I did remember them being in there. I didn't think they were, but I was deferring to your potential.
Well, they are. I mean, they are the closest galaxies not a member of the local group.
Okay.
When you're talking Andromeda and M31, M33, etc. I mean, those are like 2 or 3 million light years away, and
Yeah.
M81 and M82, I believe, are 10 or 12 million light years away.
Mm-hmm.
I was thinking they were members, but they're not.
Okay. Okay, we're going to head now back toward the south. Telescope is moving. I'm going to take us to a dusty region of the sky, which is actually in a good position to view it. It's called Dryer's Nebula. You've seen Dryer's. We've done it.
Down by the Rosette.
Yes.
Okay.
Yeah, because this whole area that we've talked about is just chock full. Okay, I can see that it's there, so I'm going to move us a little to the east here.
Yeah, that I posted that APOD image of the Rosette area.
Yeah,
Rosette was actually just a tiny little bit of it, and
that's right.
I have to guess Dryers is in that same image.
Oh, it is.
Yeah.
Yeah, absolutely. It's
Mark, will you
beautiful.
excuse me a moment, please?
Okay,
Right back.
right here. Okay. We're going to start here. We got these and this. Now, it doesn't look like much here. I'm going to also check our focus. And good thing I did. Let me I've got this marvelous autofocus system attached to the telescope, which is just beautiful. Allows us to focus very precisely. So now we can do is do it again. This should be a little quicker than typical we saw before. So the thing, one of the things that happened was when the telescope was, when we were first doing this, the telescope, we didn't know where it was in the sky. We didn't have a way to find its position in the sky. And that was quite a problem, because if we got lost in the sky, holy cow, that would mean that we'd have to go hunting for something we know before we could actually, view anything further. Well, as it turns out, I added some products and some software to this unit, this software here that you see that's doing all this. And it allows us to solve based on the stars we see, and it will automatically figure it out. And not only that, I'll show you something else it can do here in just a minute once we get our focus. It can not only find where we are, but it can actually draw what it sees on the screen, like stars and so forth. So I want to show you that. Okay, we got our focus. So we're going to go to the best focus location. Okay, and then the telescope catches up. Bang. Okay, so we are now good. So what I'll do now is back out. All right, and now if you don't know what you're looking at, we can actually come up here and let me get the where is it? This guy. Okay. Okay, so now we're going to do what's around us. We're going to actually plate solve for this region right in front of us, and then annotate, put up the details of what it sees. And there you go. So it tells you this is NGC 2247, a reflection nebula, NGC 2245, another reflection nebula, and this other big thing here, this gigantic nebula out here, right? So we're actually looking at IC 0447, See, so it tells us what we're looking at, which is really nice. And this is a new addition that I put in. I haven't been using it much with you guys because I didn't know if this would be something you wanted to see. So this doesn't affect anything we do. I can actually go and tell it to do imagery right now. Let's see, we want to do a 30-second shot of this. Okay. It's going off and doing it. And we can highlight different things in here and say, oh, well, that's this. And like this one here, let me zoom out. This is a particular star that's been highlighted. It's right here, Hipparchus 31448, and it shows you the star. The telescope knows exactly where it is, and that's what's so cool about this. So now I'll go into the live stack, right, and get rid of this stuff here, and get rid of, okay, the live stack's gone. So that's good. So now what we'll do is, now when this comes in, you'll see it. Now what's going to happen is we don't need this to be here. We can actually get rid of it and bring it back only when we need it. All right. So our full width half maximum shows 775. I should bring this up a little bit. There we go. And then now we come in here and there we go. The beginning of Dryer's Nebula. All right. So now what we'll do is scroll out a little bit more. Now, Dryer's is connected to a region that is literally chock full for many light years of hydrogen emission nebulae like this, dark nebula like this that you can start to see developing here, reflection nebula, which is actually just dark nebula that is scattering the light of stars in the blue part of the spectrum of the stars. So this dust will make the stars look cloudy, but it's just dust around the stars, and that dust is scattering the stars' blue light part of the spectrum. Let me improve this just a little bit. Okay, like right here. Look at that. Now you can see this a little better. If we go back to the annotation, you'll see that now you see it. And this gives you a very good idea of where we are. Okay, so now I'll save the image with the annotations as well. And that'll be in the directory, and it'll be out there for you to look at with these annotations on it, in case you're interested. Okay. But that doesn't hurt our image. It's a layer over the image. It doesn't affect what we're doing. So right now we have 3 frames stacked. 2 have been rejected. Let's go back and find out. Yeah, we're at 7.85. We're going to stay there. What's happening here is I'm setting the diameter or the elongation of the star I'm willing to accept. The smaller that number, the more round the star. And right now, this is okay. For some images, we can be like 5.5, 5.2. All right. For images like this, they're almost directly overhead. This means that our guiding error might be just a little bit larger, so we have to accept a little bit higher value. So I've got it at 7.85, and you can see we're coming at 7.72, 79, 78. Nice.
Might be an indication of wind also, might it not?
That is correct. And usually if we see a whole spate of red bars, we're getting wind. Right now, these two were just, I think, a failure of not having this at just the right level, because we're getting all greens now. This is all good. But yes, you're absolutely right. It's definitely an indicator of wind. look at this interesting little area right here. You see that? Okay. That right there is a fascinating location because that's got a little, almost like a little feathery shape to it. That's probably an area where there's a dust cloud and that star's light is being scattered by the dark nebula that is there. And we see it as blue because that's the light it's sending back to our eye. It's scattering the blue light in all directions, but allowing the red light to pass through it, and the orange and the green and the yellow light to pass through it from the spectrum. Because we always have, red, orange, yellow, green, blue, indigo, and violet all at once in every star, just varying amounts. red supergiants have very, very little in the blue end. It's all in the red end and the yellow and the orange. Okay? O stars have very little, if any, red component light and yellow and orange. Okay? But they have a lot of the blue and beyond into the ultraviolet. So stars don't give off just visible light. They also give off the invisible light. That is the very higher energy than we can see and capture with our instruments and our eyes. All right, this is all good. This is working. So let's see what it wants to do for color correction. All right, color correction looks good. Let's see what it wants to do for processing. It's going to lighten it up a little bit, but you can start to see there's more detail in here. This area is really pretty, Daryl, right there. I'm going to zoom in on that for a moment.
Trisha has a question.
Okay.
It's not a dumb question. She says, can I ask a dumb question? What we're looking at is live, right? Why don't the stars twinkle?
That's actually a very good question. Go ahead, Daryl. You can go after it if you want.
Well, it's nearly live, Tricia. I mean, this is a time exposure actively building and stacking as we sit and watch. So, I mean, each exposure is 30 seconds long, and he's stacked 11 so far. So that's 330 seconds worth. It is, call it near real time. Generally, we don't see stars twinkle on the camera because of this and just the nature of the optics in the telescope itself and the time exposure. We don't see them twinkle.
But the question of whether they do, if we take a picture that is within the period of that twinkling, like in the millisecond range, like let's say we take a picture at 10 or so milliseconds, and you see it on the screen. If the star is varying in its brightness in an amount that is longer than that, then you will see it twinkling on the screen. However, we set our setting at 1 second. So in that time, a star is going to twinkle many times if it's a turbulent night, and we'll just get one representation of that every second. So it's a snapshot in time. But if you watch the same star over time, right, especially if they're small, sometimes they might look a little brighter and sometimes they might look a little dimmer. So you're seeing the twinkle, but in a longer period of time, if you know what I mean. That's actually a very, very good question. Look at the details in this, guys. This black area here. This is all dark nebula. Wow.
It reminds me of a mistake they made on Star Trek The Next Generation. They had a blanket, like a black sheet covered with little specks, to show stars.
Yeah.
And they wanted to make the stars twinkle. And they did in some of the early shows, I believe. And well, stars don't twinkle in space. They're
That's
steady
right.
lights
That's right.
because there's no atmosphere to make them twinkle. They didn't seem to get that at the time.
Yeah. That's right. Michael Hedrick just made a nice observation. Thousands of stars in this beauty and clarity makes me think of how many millions of perspectives you could get in this space. Just think of how many planets and how many sunrises and sunsets there are. Yeah. In fact, when you look at all these stars here, at this point in our understanding, we can say one thing for sure, that you're looking at a lot of stars here. But all these stars, there are more stars, well, there are more planets than there are stars in this image right now. We're seeing a bunch of stars. We're probably seeing several thousand stars, and there's way more planets than there are those stars right in this image. So planets are very, very, well, they're a popular item in the universe. They really are. This is, again, Dreyer's Nebula.
Michael Hedrick again. Mark, would a fast orbit cause an atmosphere to almost buckle? That damn heart's in the way again from the sudden heat change.
Let's see what he said again. I'm sorry. I'm trying to find out why it didn't like my name. I think it'll be fine.
He amended his question a bit. Would a fast orbit, he means a fast spin, cause an atmosphere to almost buckle from the sudden heat change?
I don't know what the word buckle means here, Mike. Sorry. You got to keep in mind that we're spinning at about 1,000 miles an hour at the equator, and the atmosphere is none the worse for the wear. So, if our Earth was suddenly lowered in mass or increased in mass, then our spin rate might actually change. With all the interactions we are carrying out with the moon, we're sharing angular momentum with the moon. We're actually losing angular momentum to the moon. So our spin rate might change. And if our Earth spun suddenly faster, well, we're not equipped for that, and we would fly off the Earth. If we increase the rate, just say by a few miles an hour, you get on the scale in the morning and you're going to be lighter, and it's like, hey, look, I lost 20 pounds overnight. That's if the Earth is getting faster in its rotational spin. If it goes fast enough, however, you could jump and stay in the air for a long time like you're on the moon, because you're being thrown off the Earth at a faster rate, at a higher rate of speed, because the Earth's rotating faster. And this is all, by the way, if it increases gradually and you don't notice that the Earth is increasing in its rotation rate. Now, could that happen? No. If anything, the Earth is slowing down and continues to slow down. So what it means is that you're overall going to get a little heavier, whether you like it or not. But it'll take billions of years. So don't throw away that scale yet.
If I could expand on that a little bit.
Sure.
If you mean really fast, like planets orbiting a red dwarf star, okay, and say, those planets' so-called year is a day long because it orbits that star so fast, or, days or weeks, whatever. But even if the planet itself is spinning fast, well, excuse me, no, because it would be tidally locked to the red dwarf star. But what would that do to the atmospherics? The side facing the sun, facing the star, would get hot, and then around the edges, the terminators on the planet, the change between day and night, you're going to have a lot of atmospheric mixing, no doubt. And then you go on the night side of the planet where it's perpetual dark, it'll be cold. But you're likely to get some really interesting weather there along the terminators where the hot and cold is mixing, from day and night.
Actually, one of the theories actually goes a step further. They actually say that in such a tidally locked situation, okay, where you have this tidal locking, like for instance, here's a example. This is the asteroid Vesta, but we'll just use it for now. Let me just, while we're getting this photo, I'm gonna show the background for just a moment. Okay, so here's Vesta, all right? But let's suppose this is a planet, all right, and it's tidally locked, so this side's always facing the star, which is, say, there. Okay, as Daryl said, this side is getting heated, right? And if there's an atmosphere, that atmosphere, as it's heating, higher entropy, the molecules are all moving faster and getting farther apart from each other. So what does that do? They're not going to push out into space as much as they're going to then bleed around the edge and go into the other side. But because of the heating is focused here, what that's going to cause is absolutely cyclonic hurricane force winds at the terminator that are going to force the air around to the back, where it'll mix at the back of the star, back of the planet. And when it does that, it's pretty likely that the temperature on the back side of the very, very back side is not going to be that much cooler than the front side. And it's not like the Earth. Okay, these are small planets, and even if they're Earth-sized, they are actually getting blistering heat from those red stars on the facing side. It's like the hottest summer on record every day on that front side. And it might be that there could be some life eking out an existence there. But it might also be that with these cyclonic winds pushing into the back and mixing a lot, as Daryl said, mixing this atmosphere, the temperature back there might, on these M dwarf stars, might not reach very cold temperatures, because this front side is always being heated. It's always being heated. It's not like it rotates around the back to cool off. It's always being heated. So you've always got this cyclonic storm, these hurricane force winds pushing that highly energized wind to the back side, where it'll always be fairly turbulent. You might not have very much clear sky in the dark side of these planets, and there is truly a dark side to these planets. So it'll be interesting to see more research done on weather systems. On the James Webb might be able to characterize some of these atmospheres around these red dwarfs, which would be kind of cool. So let's get rid of that and go back. So that's kind of how that works, and I think that it'll be interesting to see more data come out about characterizing atmospheres around these red dwarf star planets. Let's take a look at this up close. Let's I'm gonna just do this. I'm gonna zoom in on that. Look at that. This is really something. This is a beautiful view of Dryer's Nebula. I'm actually quite impressed with this. Let's move this out of the way. There we are. Look at that. Let's even go bigger. Wow, look at. See, we're among the stars now, guys. Very, very cool.
I see a lot of the, I call them spider legs sometimes,
Mm-hmm.
in the dark areas on the right half of the image. I've always wondered, if those are real or if they're artifacts of the image somehow. You see that they're like radiating dark lines.
Like here?
Well, that's a big one, yeah, and that's real right
It
there.
is, yeah.
But then to the lower left of that,
Like this?
there are dark lanes with no stars in them, little skinny ones, to the left of where you are.
Like in here?
Yes. You don't see dark lanes in there?
I do.
No stars?
Yeah, I see where there's no stars in here. I see here where there's definitely a real dark lane in here. We can actually go check that out and see. Let's bring up our processor and let's do this. Let's actually crank it up. So that's what's hiding in here. Let's see if inverted will show us more. Not in this case. But what you do see is a satellite went through that we didn't catch.
Yeah.
Okay.
Christine Anderson has a follow-up
Okay.
to the. She says, Mark, is the planet Mercury like that, one side constantly heated?
Mercury is kind of tidally locked to the sun, but it's not entirely tidally locked to the sun. It goes around once on its axis every 58 days or something like that, but it takes 88 days for it to go around the sun. So it's actually not quite tidally locked to the sun. It's a very strange rotational orbit that it has. All right, but it is more tidally locked than other major planets, yes. It's probably the most tidally locked. If you call Pluto a major planet, then Pluto is the epitome of tidal locking because its moon Charon and Pluto are tidally locked in a forever dance where they're both hemispheres are facing each other forevermore on the Pluto-Charon system. And that's how the moon and the Earth will be someday. If the sun wasn't going to die and end its existence, well then, yes, the moon and the sun will end up being tidally locked when the moon got out to a certain distance. Because what's happening is the moon is stealing angular momentum from the Earth. That's because of its tugging on the tidal bulge, which is slowing the Earth down. And eventually, the Earth's going to slow down to the point where the Earth and the moon are at the same orbital rotation rates relative to each other. Orbital, as revolutions. They won't be going around at all. Like the moon goes around once on its axis every time it goes around the Earth. And the Earth goes around, 24 hours a day times 28 days. Okay, but it's actually slowing down over time. So that means that as the Earth slows down over time, because the moon is tugging on our tidal bulge and slowing down the Earth, well then it means that eventually the Earth is going to slow to the point where it will be moving at the same rate as the moon and thus be tidally locked. So you'll have whole droves of astronomers who will actually go to the other side of the Earth to be able to see an uninterrupted moonless sky at that point. If, of course, the problem with that is by the time the Earth is tidally locked to the moon, the sun will have long since exhausted its fuels and swelled into a red giant and killed us anyway. Which is a good reason for us to get the heck off this rock at some point. And we will. Stefan, nice to see you. You have a great Valentine's Day. Your next day. But thank you for coming. It was great to have you with us. He's off to work. Christine, yes, I've always felt that she writes, I'm glad you think Pluto's a planet. I do. And the reason I do is because Historically and culturally, Pluto has been a planet, and I don't want to see any crazy definition applied to Pluto when in fact it is definitely doing planetary things. It has 5 moons, all right, and these moons are circling Pluto. Okay, so planets have moons, and it's not like a Kuiper Belt object that's a binary Kuiper Belt object. Okay, we're talking about a big enough object that it has moons of its own. And although it's at a 17-degree tilt to our solar system and kind of odd, yes, it is odd. And yes, it's probably a captured Kuiper Belt, the outer belt of icy objects. Probably a captured object from the Kuiper Belt. But still, it's a planet. I've told this story before. I met Clyde Tombaugh and sat with him on a grassy hill up in Vermont. And we talked about he is finding Pluto. And as Daryl has told us many times, Clyde Tombaugh wasn't a professional astronomer. He was just an amateur with a lot of passion. And he proved his mettle and actually ended up finding a planet in our solar system. And so I don't think they should have taken it away from him.
I agree.
Yeah.
I always had a problem with the one definition of a planet the IAU used against Pluto was that it hadn't cleared its own orbit.
Yeah.
There is so darn little stuff out that far that clearing its orbit sounds like a beating with Sturm to me.
Yeah.
I mean, you're getting way out there in the sticks. There's just not a lot out there.
No, there isn't. There is not. Let me just redock that on the bottom. Let's bring back the telescope view. Okay. Look at that. That's really pretty. And look at the detail in here now. Look at the detail in here. I dare say that's more detail than we've ever had in Dryer's Nebula before. We've never been able to see all this incredible detail in here. Look at that. All these convolutions, all this dark nebula. And what is dark nebula? Dark nebula is the remnant debris from red supergiants. Betelgeuse, for instance. The reason it got dim, in the Great Dimming it was called. The reason that Betelgeuse dimmed was because they theorized that a gigantic bubble of soot and carbon-based debris in the outer atmosphere of Betelgeuse, so far away from the hot core that it could make molecules of stuff, blew off of the star and ended up getting in our line of sight for a period of time until it went away, and then Betelgeuse got bright again. And it's studying that particular explosive event that has led the Japanese team, a Japanese team, to theorize that Betelgeuse is actually going to be going supernova sooner than later, which is pretty cool. Okay. Nice. I'm reading a message here from Marianne. Okay. So, that said, we will be able to process this for you and show it to you. Our Patreon guys, the Patreon folks that subscribe, all of you that do, you'll be able to get these processed images. I'm a little behind in getting the latest images up, but I will. I'm going to swap out for the entry Patreons. You guys get 4 images, and for the high-end Patreons, you get all of our new ones. I'll just make sure that all the new ones are up there. I've got I've been working on 3 television shows, so I'm like I'm mad with work. I got several messages while we're talking from them saying, "Have you done this? Have you got that done?" You know. No, not yet. My stream family is a priority. So that's really pretty. I just look at that. That is pretty, and there's a lot going on up here. It's worth mentioning. Let me show you. All right, so you look here, and you'll see that it's sort of a reddish hue. All right, reddish hue in here. Brownish. We have everything in here. We have reflection nebula. We have subtle hydrogen emission nebula. A lot of it over on the left side of the image. And then we have dark nebula that's showing us brown. Really cool. Beautiful. That's going to be really pretty when we do processing on that. Wow. So you guys having a good time? Okay, we're at the 42. This is Dryer's Nebula. We're going to save it. Save it exactly as seen. All right. I think I'm going to go back over here because I may do something crazy. Let's center up on that. Yeah, because if we go to the left, that takes us into the Christmas tree cluster and Christmas tree nebula, the Phosphor Nebula that we see there. We have Hubble's Variable Nebula. We should probably take a shot of Hubble's Variable Nebula because we always look to see what its brightness is doing, don't we? But I'll skip it because I don't want to change the camera settings right now. Let's see. We're still exposing here, but I'm going to look for something else. Okay. Yeah, this is right near us. We're going to do this one. This is one that was asked for by Cosmic Ray. And that'll be the next one we go to. It's called Lowers Nebula. I have never met Vera Rubin, no. I did apply to work on the Vera Rubin telescope, though, but I would have had to go to Tucson. And they were looking for someone with different experience than I had. So I didn't get that position, but that's okay. Okay, this is 46. We're going to save it here. Save it exactly as seen. Ah, that's pretty. I can't wait to go play with that one. Alright, and that's Dryer's Nebula, guys. Okay. In a telescope, you'd never know it was there. You might see some subtle nebula around a star, maybe. But you might be able to see, with a bigger telescope, little nebula like that. But you're never going to see all the dark nebula we saw with a regular telescope at all. Okay, so now, by request for Cosmic Ray, and this was from several sessions ago, I just didn't forget, we have Lowers Nebula coming right up. All right, Lowers is right here in the middle. And we'll call it what it is. I don't believe I've seen this before, so this will be a new one for me. We'll make it a 30-second shot, which is 30,000 milliseconds. first things first, let me just check our system. We actually have to wait about 11 to 12 seconds to catch a guide star, and after that it'll start guiding. Okay, when you see the numbers show up, we're guiding. There we are. All right, let's go. So we're gonna take this down, jump into our live stack, clear the last one. Where we are is actually to the right of this. That's actually where we are. I'll show you here. Here's Lowers Nebula.
Spell that, please.
Yeah, Lowers. There it is. Look at that. That's going to be a beautiful little nebula. Thank you, Cosmic Ray, for that suggestion. Look at that. Beautiful. And let's do this for initially, and then we'll pull it back in. So these are the red, green, and blue curves, and I aligned all the curves under each other so that sets the color properly. And the average is this white curve you see. This yellow curve is actually the curve that shows the actual data that we're using, right? So if I move to the left, we're moving more of the data under this curve. We're moving more in so that it gets brighter. And as we approach the peak of the curve with the black level, just before we get there, this makes it the darkest we can get without losing data. Technically, hey Hunter, my son just got home. Now technically, as we move this a little bit closer, as long as we stay to the left of the peak, we don't lose any data. However, we get into the left of the peak or into the right of the peak, and we will. Moving these closer together now moves more data from the other subtle regions in, and now we'll actually see more data on the outside that we might not have seen. So by adjusting these two, we get to show you the coolest stuff and as much data as possible.
Description here says Lowers Nebula is found on the outermost edge of our Milky Way between the Orion and Perseus arms.
Okay.
Doesn't say how far it is, but it's out at the edge of the galaxy, evidently.
That's pretty cool.
I think it would mean it would be really big.
Let's go to it again specifically. Yeah, we don't have a distance for it.
Yeah. Looking.
Yeah, it may not be. May not have one. See, when we look at galaxies, you know, you wonder, well, how do we know how they're rotating? How do we know how much they're rotating? You know, how is it possible to even measure that? Don't you have to wait a long time to see anything happen? Yes, and we don't. We don't need to. And why is that? Because the light is encoded with everything we need to know. When we look at let's take, for example, the 21 centimeter neutral hydrogen line. That line, you see that in the hydrogen, in the arms, the hydrogen gas. Those arms have all this neutral hydrogen atoms in it, all these neutral ones, and as it's rotating towards you, the spectral line, which is in a specific place for neutral hydrogen, is actually shifted toward the blue end of the spectrum a little bit. And on the other side of the galaxy, the hydrogen line is shifted toward the red as it's going away from you. And that tells you the rotation rate, the speed at which that spiral arm is moving. And that's how we figure out the speed of rotating galaxies. It's also how we can find how much a nebula is changing. We can do a study of its neutral hydrogen to see which direction it's moving, where it's coming to, where it's going to. So that's, and there's a lot of neutral hydrogen out there, right? Tons of it. And that stuff is, and the thing is, once the movement is occurring and the neutral hydrogen line, the spectral line, is encoded with this blue shift or red shift, that's not going to change. That's not going to change. So it'll always, well, at least for our lifetimes and probably several 100 lifetimes, it'll stay the same. So we'll have the opportunity to see this already encoded data. So by looking at this already encoded data in the light coming to us, we can make a lot of rather brilliant deductions about the universe. I'm with Tricia Ferreira. This should be called the Kiss Nebula.
Looks kind of like a clam to me.
A clam. I guess it could be. Cosmic Ray mentions that the three bright stars, I believe it's probably these stars, are exceedingly blue. They might be blue, and I think what I'll do is I'm going to come in here a little bit, and let's click on one of them and see what we got. Okay, we don't have a spectrum on that guy. How about this guy? Oops. Let's try this one. Yeah, that's an 07. So Ray, this is one of the cluster stars in here, and these probably are as well. This one, I don't know if this is going to be one. Let's find out.
Ray, mind you, in that SHO palette, hydrogen is blue. So, I mean, the natural color of hydrogen is red. Hydrogen alpha is red light.
Yes.
So, that's a classic example of false color, maybe leading you astray. SHO sulfur is red, hydrogen is blue, oxygen is green. Or do I have that backwards?
No, I think you're no, sulfur is red, hydrogen alpha is red, oxygen is green.
But in the SHO palette, the assigned colors,
Okay.
sulfur is red, and hydrogen is either green or blue, and oxygen is either blue or green.
I believe the hydrogen's green and the oxygen's blue. They're different colors, just to differentiate them, yes. Let me... All right, so we're still building this one up, And we're at 17 exposures. None have been rejected, so we're making good progress. I'm liking it. Are there any other questions in the chat right now for us?
I'm not looking at chat at the moment. I'm
Okay.
looking something up.
Alrighty. All right. I'm going to I'm going to look at, there we go, that's what I want to see. And I'm going to try a little housekeeping thing here, and then I'll be right back to you guys. All right. All right, we are at 20 exposures here. Actually, this is not a bad nebula to be imaging right now, huh?
Actually, it's very nice.
It is. It's got a very, very nice coloration. And let's see if a color correction does anything. Yeah, we're good. We're good with color. And this guy here, it's probably going to want to move it apart like that a little bit. Softens up things. I like pulling out the brightness of that red a little bit more. Just showing it. Making it a little bit more obvious. And I like bringing this right to the upper part, just to the left of the peak. Like that. And that's really pretty. That's stunning.
It's nice.
Yeah, so what I'll do now, while we're here and doing this, I'm going to do the deep sky annotation on this. Now the last one is going to be listed, so we're going to change it to what this one is. So it's searching for the new one. And it doesn't. That's funny. It finds that, but it doesn't find it. Interesting. That doesn't mean it's not there. It means that Lowers Nebula is not in the database. Depends on its designation, but that's okay. Not everything is in that database. This is going to be really pretty. We're going to probably see, again, these are hot O-stars in here. You can see what's going on in here, just like we talk about with the rosette. These hot O-stars clear a cavity in here around them, and that's what we're seeing. Clearing a cavity.
Lowers Nebula is also known as Lynn's Bright Nebula 863.
Okay. Oh, that's really pretty, I have to say. I like it that. I like it that.
LBN 862.
Mm-hmm. Yeah.
Nobody sees a clam there? Reminds me of one of those big giant clams down on the ocean bottom.
Yes, I guess it does. It certainly does. Without a doubt.
Like a frog with its mouth open, maybe.
Or it looks like a kiss on Valentine's Day.
Well, don't blame me.
Wow. Okay. Well, I think that Trisha Ferreira's observation is pretty good one. You know, it looks like a kiss, and it's the right day for it.
So
Let's
you
see.
were the one that wanted to go to the Heart Nebula. Don't blame me.
Oh no, I know. I got my Valentine's Day nebula. And I'm glad that we didn't do it last time, because this way Cosmic Ray's the one that suggested this, and so now he gets to see Lower's Nebula. That's pretty cool. You can clearly see the cavity being made here. Look at the curvature and everything. Clouds here of gas, hot ionized gas. It's quite a sterile region in there, I can tell you that. There's not a whole lot of dark nebula to protect a young planet forming. But go ahead.
I only see hints of the color difference here, but in that cavity area, in the SHO image, that is all really bright blue in there, which I guess signifies oxygen that maybe we're seeing just a hint of here.
Well, actually, if it's going to sound funny, but if I leave it right here, if you look at the center, and now what I want you to do is look over here, or even here, okay? And if you do this, folks, you'll see that this here kind of looks reddish, but when you look here, if you look right here, your eye is picking up a different tone here, which is kind of bordering on green.
Yep.
And so you're actually seeing potentially O3 oxygen atoms that are ionized inside here, which is also like the rosette. Very interesting. This is very nice. I'm liking this a lot.
I see Barney Rubble now.
Hey, Fred. Yeah. Hey, Bon. Really pretty. This is nice. Okay. 33 is good. Save. And save exactly as seen. Wow. And let's back out and just get an overall view of it one more time.
I think that's actually probably the nicest picture tonight.
Yeah. That's really nice. This isolated, beautiful, stellar nursery. Michael Hedrick says, will you take some images like the Pleiades and M32 and Andromeda and nebula like this, and bubble, etc., and make a book? Oh, we're actually talking right now with another member of our SkyTour family who is interested in exactly that, we have to talk to her about that. That's Izabela, because Daryl and I and Izabela have talked about actually making a book that might be a really cool book to show people things, talk about them, explain how they form, and just be a beautiful picture book, like a coffee table book. Remember that, Daryl?
Yes.
Okay.
crossed my mind the other day. Hadn't heard any talk about it in a while.
I know, that's correct. We kind of let it drop, and that's not... I don't want that to drop. This is too good to drop. Okay. Well, there's Lowers Nebula. And now we're going to exit Lowers Nebula in our spacecraft and head to one more object of interest if we can find it. Well, not if we can find it, but... If you notice, alright, let's just back out a little. I want to show you something. You notice that Orion is now in the southwest. Way over in the southwest.
Yep.
Yeah.
I looked last night. Orion was setting at 1 a.m.
Wow. Well, it's 9:38 out there. Oh no, it's not. It's 10:38 out there. No, wait.
10:38.
Yeah, 10:38. Yep.
Same time as here.
Yeah. Okay, so I want to see
Lepus there to the lower left of
yeah, right there.
Orion. That's a rabbit. Maybe that V there. Yeah, that's his ears. See the ears of the rabbit and the stars?
Yeah, Lepus is like Orion, is kind of looks like what it's supposed to be. At least that's the way it's supposed to look. Now, let's I think we've tried this before. And let's see if we can catch this. Okay, we're going down there. What's that guy? The albino butterfly. I remember that. Okay, this is a cluster associated with the velocity nebulous detail. So what I'd like to do is check it out. It's sort of akin to dryers. And we're going to just go north a bit. There we are. We're going to wait for it to get in here. That actually might be there. Let's find out. Let's do 25 seconds. And let me drop this down. Go into the stack. And we should have the previous one in there. There's lowers, and you can see that the colors in there are different. Okay. Okay, that frame was rejected. Let's find out why. 7.9. Oh, so close. Oh, let's try. Just go a little bit higher, not much. Here we go. Oh, it's up there.
It takes an imagination, Ray, that's all.
What'd he say?
You should really sell the stuff that Daryl is smoking to see all the stuff he sees. Natural talent, Ray. Sorry.
Okay, this nebula, I don't think it's going to be terribly exciting. So I hope you don't mind, but I just had to check it out.
Well, they're serious. Check out M41.
Oh, down here we have the little beehive. This is Measure 41. That's a pretty cluster. It's one of the favorite clusters.
Yep.
It's a favorite son. All right, we'll come out of this. All right. And we're going to go out of this. And we'll go to Sirius. I just noticed a little wind over there. All right. Now we'll go. We should see this. You'll see the telescopes moving now. And we will see. Yeah, I can't miss it. Blam. What's interesting about these clusters is that when they're born, they're surrounded by gas and potentially dust that they formed within as well. But over time, they're moving, and the dust that they were formed in tends to be pushed away by the stars. Just like we saw the cavity being built by those O stars in the cluster, these stars will also mature and push away their stellar nursery over time. And this is why it ends up looking like just an isolated cluster in the sky. It didn't start that way. This used to have a nebula around it at one point. And now it's just this. Now, in some cases, the cluster could move independent of the nebula at a certain point in time. But usually the stellar winds from these clusters are pretty intense, and they will push the material away. All right, let's do a 25-second shot of this guy, because it's really pretty. Okay, let's clear this one. And I'm at 7.85 on my full width F maximum correction. Let's see if it's enough. No, it's at 8. We're gonna see what that does. I'm willing to go 8 and no higher. I bid 8. I can't go any higher than 8. It's okay. We weren't guiding quite right anyway at that point. See, that makes sense because we weren't really guiding well. All right, now we're guiding. I'm going to predict this. Well, I don't know. Maybe. I'm going to guess this image is going to come in fine, based on the guiding rates I'm looking at. Yeah, it's getting lower, but not low enough. All right, well, let's
Maybe
go.
You ought to move north again.
What do you mean?
Well, as you said, looking at M81 the other night,
Oh, I see
and
what you mean.
earlier tonight when you were farther north. I mean, you were down in the 5s.
Yeah.
Get down here around the celestial equator, and you're getting up in the 8s and the 9s.
Yeah, and I could probably just move this up to where I should be able to see it. Yeah, and that correction is going to change depending on where we go. So, wind made that 9.25 that we see there. Let's try this guy. All right, here we go. Hey, not bad. That looks pretty, huh?
Mm-hmm.
I see a lot of red supergiants possibly in this cluster.
Yep.
Similar to double cluster in morphology, maybe.
Yep.
And now, correction of the colors. Let's bring this dark level up higher on our peak. Just before the peak. Yeah, very nice. Now that's just a beautiful cluster of stars. This is called Messier 41, or the Little Beehive.
Mark's point about the red stars. Cluster stars tend to be the same age and the same type. And we have seen elsewhere, like in the double cluster he mentioned, that in older clusters, we'll sometimes see that some of the stars have already started evolving off the main sequence and are no longer the colors of their brothers and sisters, but they've turned into red giants or supergiants.
Yeah. And we might be seeing that here. I can't say we are for sure because I haven't studied at all this particular cluster to know the distances to many of these stars. If these red supergiants are outliers, they could be part of a cluster up here in the foreground that's evolved, and those stars are back here, you know, that are evolving differently on their own. But they're based on what I'm seeing, they're probably part of the same cluster.
Give me a second, I'll find out.
All right. Hey, old school, how you doing? Hey, Marco.
Yes, the red giants belong to the cluster.
Cool.
They're type, the brightest one is a K3.
Okay.
Clusters 25, 26 light years across, 190 million years old.
Mm-hmm. Trisha, I have an answer for you for your question. I'll let Daryl finish first before I read your question and answer. Is there more?
Walter Scott Houston said, many visual observers speak of seeing curved lines in Messier 41. Although they seem inconspicuous in photographs, the curves stand out strongly in his 10-inch reflecting telescope, and the bright red star near the center
There's a
is
curve.
prominent.
Most people have seen this curve I'm outlining right now. Right here. See? That's pretty cool.
Tricia, to answer your question, I don't know.
I do.
I hope he had a sense of humor.
I'll tell you who. Several. I would have loved to have met Harlow Shapley. I would love to have met Edwin Hubble. I would love to have met Fritz Zwicky. Zwicky, named for the Zwicky Transient Facility that hunts for things. Famous Swiss astronomer. His daughter Barbarina will often come in our streams. And I did meet Clyde Tombaugh, the founder of Pluto. And I've met other Bart Bach. I met Bart Bach, famous for Bach globules. Actually, Bart was a professor I had when I was getting my degree in astronomy. for a period of time. I met a number of people that Stephen Jay Gould. I met a number of folks that were really something in the astronomy field.
Stephen Jay Gould was not an astronomer.
No, he wasn't. But he had a lot to say about astronomy.
He had a lot of things to say about baseball, too.
Well, I never talked to Stephen Jay Gould about baseball.
He was a sabermetrician. That's someone who studies baseball statistics. He was a biologist, wasn't he?
Yeah, he was a biologist, and he went into astrobiology too, as well as anthropology. He had a lot to say about anthropology, if I recall. A fascinating guy.
Oh yeah, I read all his books. Every book, there's at least one baseball story too.
Yeah, we're going to get 10 images here and then we'll stop. Because we're going to compare this one with the beehive itself. First of all, let's see if this cluster, the little beehive, it's 2,300 light years away. Okay, all right, we got 10 with 10 rejections. Okay, so we'll save exactly as seen. We got M41, the little beehive here. That's beautiful, guys. When you see this with some processing to literally, let's see if we can kind of approximate it here. Yeah, it'll look something like this. Ugh, stunning. Wow. Oh, we got 11 there, so I'll save it. And save exactly as seen. Good. Nice. Okay, so we'll come out of this. Go back here. 1 second low light shot. And check out the little beehive like it would look in your telescope. Okay. And now,
Who would I want to meet? Tombaugh. I've heard, like he said, he was a nice old guy.
he's a really good guy. Yeah. I enjoyed his company.
I think I would have liked to have met Carl Sagan. Maybe.
Yeah, yeah, Carl Sagan's a good one.
Edwin Hubble,
Yep.
from what I've heard, was something of a stuffed shirt.
I still want to meet him because he made history.
He was a homeboy. He was born and raised in Marshfield, Missouri, and that's just a little bit northeast of my hometown.
Wow.
But he grew up and got out of Marshfield, and I don't think he ever went back.
Probably not.
He was he moved in wildly different circles. Isaac Newton, I don't know if it's really fair to call him an astronomer. He did invent the Newtonian telescope. You talk about a stuffed shirt. Newton was not a nice person. I would like to have partied with Tycho Brahe. He had a silver nose.
Yeah.
He lost his nose in a sword fight, so he had a silver one made. He was a party animal.
Yeah, I would. If we're going back that far, then I would have enjoyed shadowing Leonardo da Vinci to see how his thought process worked. Okay, here is the beehive cluster. Let's move a little to the west. A little to the north. Okay, get the rest of it in here. This new camera, its field of view is basically the beehive. Alright, that's good.
One thing the beehive and the little beehive have in common, they were both known to the ancients. This is sometimes called praesepe, or the manger. The ancients knew of it, and Aristotle supposedly saw the little beehive, Messier 41, we looked at just before this.
Yeah, well, the truth is, that would not be something that would be unheard of, especially where you had no light pollution.
Yep.
Right,
Oh,
so there's
sure.
M41.
They knew of Messier 8, the Lagoon Nebula. Lots of deep sky objects that were naked eye back in the day.
Yeah. So there's M41. And our next photo should be praesepe, or the beehive. And it a little bit high. Let's wait one more. Wait a tick. Okay, it's going to be pretty high. I wonder why. We're facing right up, so it might be wind.
Yeah, you're looking pretty high. You're right between Leo and Gemini right now.
Yeah. When Leo gets up higher, we'll have some wonderful galaxies.
Yeah.
We're going to catch praesepe here, so let me just...
Cantor's right on the meridian here. That's where the beehive is.
Yes. Right dead center in the Y almost. Okay. So let's tighten up our curves, and then let's correct. I'm sorry, then let's do this. Now, you'll see that this apparently has some red giants in it, or K stars, which I'm sure you can look up for me right there, Daryl. That is pretty wild. We're almost, as you can see, this is pretty beautiful cluster. Significant giant stars here, potentially.
What would you like to know?
I just want to know if these red stars are red supergiants in this cluster. If you could look that up. And over here, I suspect they are. So this is another aging cluster. Ronald, you asked what would this look like in your binoculars? It'd be stunning in your binoculars. You shouldn't be asking, you should be doing. Go do it. where you are, it's probably right up straight toward the south, high up in the not high up, but just well, look where the telescope's pointing. You're a little further north than me, with the telescope, I should say. Were you able to find anything on Beehive or no?
Say again?
Were you able to find anything about the beehives?
Yeah, I'm looking at it right now. Give me a moment.
Okay. Hey, how you doing there, Vince Giglio? Just saw that you're here. Old school, I see you here. Of course, I said hi to you, Ronald. How you doing?
There's about 1,000 stars in the cluster. They've experienced mass segregation, meaning that the bright massive stars are concentrated in the core. Dimmer, less massive stars are out in the outer part. There's 68% are M dwarfs, 30% are sun-like stars, spectral classes F, G, and K. 2% are bright stars, spectral class A. Also present are 5 giant stars, 4 of which had spectral class K0 and the 5th G0. 11 white dwarfs have been identified in the cluster.
All right.
Probably, that, I guess, another sign of the evolution of the stars off the main sequence and getting old.
Yeah, I mean, and their mass drives how soon that happens.
Right.
If they're more massive, then they more quickly eat up their hydrogen fuel for the main sequence hydrogen
Right.
burning.
They were originally spectral type B. Two planets in the Beehive cluster.
That's cool. Oh, good night, Christina. Or
So,
Christine.
I guess you could say, yeah, like M41 or the double cluster, the bright red stars are more evolved members, and the white dwarfs have evolved so far that
They
went
were
from
red
class
giants.
B stars down to white dwarfs.
No, they went down to their red giant. They went out to the red giant stage, and then they contracted down to white dwarfs.
And it's an old cluster, and so if they went through a planetary nebula phase, I guess they've long lost their luster there. Good
Vince-
night, Christine.
Vince Giglio says, just got my full spectrum converted camera back, waiting for a good chance to take it out. Heck yeah. What he means by that is if you have a regular camera that you buy, a 35mm camera, a digital camera, they have what's called an IR blocking filter in them. And they also have a UV filter in them. If you take out the IR filter, then you're going to get a disproportionate amount of that extra red light that's down in the near infrared spectrum. And so every picture you take of, say, trees or a landscape, it's going to look pink. And so you get a full spectrum camera, and you're going to end up with these pink images because that dominates the view, and because you're getting more infrared. Now what you can see with that, if you get a star analyzer, it's a small gradient that you can attach to your camera. I did that. You can actually photograph the spectra of stars and identify the stellar types by their spectra, which is really cool. And but you see something else when you point it at a star. In all of the spectra you get, you also get these other dark bands in the spectrum out in the red end of the spectrum. And you go, what are those? Those are actually called telluric lines. Those are actually the Earth's atmosphere polluting your stellar spectrum. And so you have to remove those if you want to look for stellar spectra purely, which is kind of interesting. Okay, we're at 17. This is good for this one. That's good. All right, save exactly as seen.
The ancient Greeks supposedly saw 2 donkeys eating out of that manger.
Man, I don't know what drugs they had back then, but boy, they must have been powerful. I believe it, though. When you don't have light pollution, anything's fair game, right? Wow, not bad. All right, well, let's see. While we're here, we're going to go over here, and this will be our last object tonight. One more cluster. Okay, we saw Messier 41 in Canis Major. We saw M44, the beehive. And now we're going to see Messier 35, another cluster. And what's interesting is it's right next to another cluster that we see here. And this one is farther away than this one. This is another young cluster of stars. And as we take a nice photograph of it, we'll do 25 seconds. All right, let's do that. Okay. And now we'll come back into our stack and look at the beehive cluster one more time before we get rid of it. So there's the beehive. It looks similar to Messier 41. All right. And now, in 5 seconds, our next one should come in. This value of 9.86 should still be usable for this. We're going to find out. There we are. Good. Look at that. And we are in a more populous area right now. And you can see that right there. We're at 747. That's actually pretty good. I'm going to drop this down. And we'll see if we can maintain that. Not bad. Yeah, we got 2. So this cluster is I gotta remember if it's 2187. I'm not sure. I gotta see. 2158. Okay, so we have Messier 35, and we have NGC 2158. If we look here, NGC 2158. It's a very rich cluster, but it's far away, and we don't have a listed distance to it, unfortunately, but that's okay. Let's go back here. Okay, Shoebuckle cluster, or this one, is a distance of 2,772 light years. NGC 2158 is going to be much further away. And part of the reason you have an inkling that it's much further away has to do with looking at it visually. There's a couple things you can deduce. One of them is you'll notice that the color of the cluster is markedly more yellowed, overall than, say, this cluster here. Why is that? That's because this is through being seen through dust. Here's some dust right here. And you're seeing this cluster through dust. And whenever you get that, you get reddening. It's called interstellar reddening. And it happens in the same way that the sun gets red on the horizon when it's sunset. You're seeing it through more air. And the molecules in the air tend to scatter more of that blue light we talk about. And the dust in the universe scatters the blue light as well. So the blue light from the sun being scattered in every direction is why we have a blue sky. Now, we don't see any blue nebulae, but that's okay. Scattering is still taking place, although at a level you can't readily see. But you can see that these stars are all reddened, every one of them. If it was just a couple of them, well, then that can be due to their color. But overall, this means it's a further cluster, and it's reddened because it's farther away.
It's also very old. It's 11,000 plus light years away. M35 is 2,000.
200 and
this one
something.
is 9,000 light years farther, or 11,000 plus light years.
Yep.
And it's 2 billion years old. Cluster is. That's a very old cluster.
Yeah.
Open cluster.
Thanks for looking that up.
Yeah.
Very cool. All right, we're going to go to 10 on this. As this is a remarkably rich area. And M35 has some red giants in it too, it looks like. And 2158 looks like it has its contingent of some red stars in it as well.
I've said before, looking at that, it looks like there's a horizontal row of stars across the face of 2158.
Interesting.
You don't see that?
You're talking about this right here?
Yes.
Yeah, that looks like a horizontal row, yeah. Yep. Very cool. Wow. Well, guys, I hope you've enjoyed this. I'm actually gonna make a note this one, and we're gonna process it. M35 OC, and after that, I'm gonna say NGC. GC 2158. There we are. And now with a dozen exposures, we'll save it. Save it exactly as seen.
Oh, you see, I see those spider legs all over this picture too.
Yeah, I see some here and some here and there. I mean, those could just be your mind, or they could be dark nebula in there, or simply a gap in the stars.
Yeah, go figure.
Ronald asks, that'll be the last question of the night. If you could go anywhere in the universe, where would you go? Well, I wouldn't go to a hot young cluster. I wouldn't go to a hot nebula. I'd probably go to a dark nebula off in the corner of the universe somewhere where new stars and planets are being born in the dark. Because that's the best chance for life, is in the dark.
Assuming I was in a good spaceship that had good life support, shields and all that,
You're going to go to a black hole?
No, I'd go to the Orion Nebula probably.
Hmm.
Go to the trapezium.
I think you'd be disappointed when you got there, because I suspect when you got into the nebula, you wouldn't see any nebula around you at all. Because it's so sparse in reality. It only shows up at distance.
I knew you'd say that.
Excellent. All right, I'll say it one more time. Hey, folks, thanks for coming tonight. Really enjoyed your company. And thanks for putting up with a little bit of the issue we had at the beginning. But we're good. We're good. You know, as long as you have procedures in place. Hey, you know, when Apollo 11 landed on the moon, they received a 1201 alarm. That was that the computers are supposed to land the lunar module, but the 1201 meant that they had to land it manually. So it was like 1201, Roger, 1201. And he took control, and they landed like nothing because they practiced it. So as long as you have procedures, then you can recover from anything that may go wrong. And so we try to have them, and I try to just calmly go through the checklist, right? Anyway, you guys have a good night, and we will see you again real soon. But it's been great having you with us. Thank you for coming. So we'll talk to you later.
Good night, everybody.
So long, everybody.